Have you ever looked up at the clouds and wondered, where does all this rain come from? And why does it seem to rain more in some places than others? Well, today we're diving deep into the fascinating world of rainfall, uncovering its hidden patterns and exploring how we predict one of nature's most vital phenomena. Let's start with the basics. The journey of a single raindrop is part of the amazing water cycle. It begins with evaporation, where the sun's heat turns water from oceans, lakes, and even plants into vapor. This invisible vapor rises into the atmosphere. As it gets higher, the air gets colder, causing the vapor to condense back into tiny liquid water droplets or ice crystals. These droplets gather together to form the clouds we see. When enough of these droplets clump together, they become too heavy to stay suspended in the air and fall back to earth as precipitation, what we call rain, snow, or hail. It's a continuous loop, a global recycling system that's been running for billions of years. But this process isn't the same everywhere. Global circulation patterns play a huge role in determining who gets the rain. Think of the Earth's atmosphere as a giant engine powered by the sun. The equator gets the most direct sunlight, heating the air and causing it to rise. This rising, moist air cools, forms massive clouds, and releases heavy rainfall. This is why tropical rainforests like the Amazon are so lush and wet. As this air rises at the equator, it gets pushed towards the poles. Around 30 degrees latitude, north and south, this now cool and dry air begins to sink. Sinking air warms up and prevents clouds from forming. What do you find at these latitudes? The world's largest deserts, like the Sahara and the Australian outback. It's no coincidence. It's a direct result of these large-scale atmospheric circulation cells known as Hadley cells. So, this same system that drenches the tropics is also responsible for creating our planet's driest regions. But what about areas that aren't at the equator or 30 degrees latitude? Other factors come into play. One of the most important is topography, the shape of the land. When moist air blowing from the ocean encounters a mountain range, it's forced to rise. As it goes up, the air cools, and just like at the equator, the moisture condenses and falls as rain on the windward side of the mountain, the side facing the wind. This is called orographic lift. The result? One side of the mountain can be incredibly green and wet, while the other side, the leeward side, is left in a rain shadow. This side gets very little rain because the air that descends on it is now dry. A great example of this is the Sierra Nevada mountain range in California. The western slopes are covered in forests, while the eastern side is a desert. Ocean currents also have a massive influence on rainfall patterns. Warm currents, like the Gulf Stream in the Atlantic, bring warm, moist air to nearby landmasses. This is why Western Europe is much milder and wetter than other places at the same latitude, like parts of Canada. Conversely, cold ocean currents, like the Humboldt Current off the coast of South America, cool the air above them, reducing its ability to hold moisture. This contributes to the extreme dryness of the Atacama Desert, one of the driest places on Earth, even though it's right next to the massive Pacific Ocean. Now, let's talk about some of the big-name climate patterns you might have heard of, like El Niño and La Niña. These aren't just weather buzzwords. They are powerful, large-scale phenomena that can temporarily rewrite rainfall rules across the globe. They are part of a cycle called the El Niño Southern Oscillation, or ENSO. Under normal conditions, trade winds blow warm surface water from the eastern Pacific near South America towards the western Pacific, near Australia and Indonesia. This piles up warm water in the west, leading to rainy conditions there, while the eastern Pacific is cooler and drier. During an El Niño event, these trade winds weaken or even reverse. That warm water sloshes back across the Pacific towards South America. This shift in warm water dramatically changes weather patterns. Regions that are normally dry, like Peru and the southwestern United States, can experience heavy rains and flooding. Meanwhile, places that are usually wet, like Indonesia and Australia, can suffer from severe droughts and an increased risk of wildfires. La Niña is essentially the opposite. The trade winds become even stronger than usual, pushing more warm water to the western Pacific. This intensifies the normal pattern, making places like Australia even wetter and the southwestern U.S. even drier. These cycles happen every few years, and their effects are so significant that meteorologists and climatologists around the world track them very, very closely. So, how do we take all this information, the water cycle, global circulation, topography, ocean currents, and massive climate patterns like ENSO, and turn it into a reliable weather forecast? This is where modern weather prediction comes in, and it's a monumental task. It all starts with data. A massive global network of weather stations, weather balloons, ships, buoys, and, most importantly, satellites are constantly collecting information about the atmosphere. They measure temperature, pressure, humidity, and wind speed at various altitudes and locations. This creates a detailed, three-dimensional snapshot of the atmosphere at any given moment. But a snapshot isn't a forecast. To predict the future, all this data is fed into some of the most powerful supercomputers on the planet. These computers run incredibly complex numerical weather prediction models. These models are essentially sets of mathematical equations that describe the physics and chemistry of the atmosphere. They use the current state of the atmosphere as a starting point and then calculate how it will evolve over time, hour by hour, day by day. The models simulate everything: how the sun will heat the ground, how winds will move air masses, and, crucially, how and where clouds and rain will form. Because the atmosphere is a chaotic system, where a tiny change can lead to a big difference later on, forecasters don't just run one simulation. They run an ensemble forecast. This means they run the model dozens of times, each with slightly different starting conditions. If most of the simulations in the ensemble predict rain in a certain area, forecasters can be much more confident in that prediction. This is why you often hear forecasters talk about a % chance of rain. It's a reflection of the confidence level based on these ensemble models. Short-term forecasts for the next few days have become remarkably accurate thanks to these methods. Predicting rain a week or more in advance is still challenging, but the science is constantly improving. And it's not just about knowing whether to carry an umbrella. Accurate rainfall prediction is vital for agriculture, helping farmers decide when to plant and irrigate crops. It's crucial for managing water resources, ensuring our reservoirs have enough water for cities. And it's essential for disaster preparedness, giving communities early warnings about potential floods or droughts. So, the next time you feel a raindrop, remember the incredible journey it has taken. From the sun's energy lifting it from the ocean to its trip through vast atmospheric currents, its path shaped by mountains and ocean temperatures, and finally, its arrival predicted by supercomputers processing billions of data points. It's a beautiful and complex dance of physics and nature that connects our entire planet. Understanding these patterns not only helps us predict the weather, but also gives us a deeper appreciation for the intricate systems that make life on Earth possible. Thanks so much for watching. If you found this journey into the world of rain as fascinating as I do, don't forget to hit that like button and subscribe for more deep dives into the wonders of our world. See you in the next video.